Thank you for watching this video. I'm ChingKai. Now I am the Max Planck UBC postdoc fellow looking for a new postdoc or faculty position in North America. Although my CV and the writing of my research statement has shown my skills and my research interests, I believe that this video will talk about a complete story about my past, current, and future research. Research is important, but my research clearly is also important. There are two directions of my research. First, Magellan fermion in condensed matter physics. Second, topological insulators and superconductors. When I was in UIUC, I was working on Magellan fermion in superconducting topological insulator with Taylor Hughes. In UBC, I have studied Magellan braiding with Marshall friends. Now, my interest extended to interacting systems. My main focus is interacting in topological superconductors in two directions. First, I'm interested in topological superconductor system without U1 symmetry breaking. That is, without using mean field theory, fermion interaction state. The reason to study this is that I believe if we put a topological superconductor in particle number conserved box, the physics won't change. What is Magellan fermion in many body wave function with U1 symmetry? That will be an interesting question. Second, in pure Magellan fermion systems, we study the interaction of Magellan fermion instead of a regular fermion interaction. For topological insulator and superconductors, first I studied the tenfold classification of a topological insulator and superconductors with my former advisor Mike Stone in UIUC. Later, from the tenfold classification, I, with Hong Yao and ChingKai Lu, extended the classification to the refractional symmetry topological insulator and superconductor. As a Max Planck UBC postdoc fellow, I have cooperated with Andreas Snyder in Max Planck. We have extended the classification to refractional symmetric topological semimetals and nodal superconductors. Now I am writing an article of Review Modern Physics with Andreas, Jeffrey Deal, and ChingKai. The title is Classification of the Topological Quantum Matter with Symmetries. I have done a lot of classifications already. Andreas and I are looking for some materials as crystallized topological matters. We are studying anti-perovskite materials now, which might be a candidate of the refractional topological insulators. I have studied two possible experimental setups of Magellan fermions. First, Magellan fermions are in the vortex ends of the topological insulator and the superconductor proximity heterostructures. This heterostructure was first proposed by Fu and Ken. We investigated how the vortex sets of magnetic flux affects the energy of Magellan fermion in this setup. This figure shows the distribution of Magellan fermion in different vortex sizes of the magnetic flux. It turns out that when size is too small, smaller than one blockhead, Magellan fermions at top and bottom couple, as shown in this figure. The Magellan fermion penetrate the bulk to couple. The energy of Magellan fermion is not zero now. So to have zero energy, the size of vortex should be big enough. This figure shows when vortexes increase, Magellan fermions decouple and the energy is reduced to zero. Lambda is the vortex size of magnetic flux. These figures show that when vortex size increase, Magellan modes at the top and bottom are separated. Secondly, we consider the setup of superconducting doped topological insulators. Similarly, the Magellan fermion modes are in the vortex ends. Our study is slightly different from the original study. We consider additional trivial bands. It turns out the trivial bands stabilize the Magellan modes. The figure shows that the topological region of a chemical potential with trivial bands is much larger than the original model. This is the original model. This is the model with the trivial band. The more larger topological region, the more stable Magellan fermions. I am also working on braiding protocol of Magellan fermion systems. Our recent studies show it is possible to exchange Magellan fermion in strictly one-dimensional structures. We propose two possible protocols. First, it is one-dimensional Kitaf model. This is the topological region. A Magellan mode at each end of a topological chain. We move the pi domain wall from one end to the other end. Our recent paper shows that these two Mahjong modes can exchange with some fine-tuning. Furthermore, we consider a more feasible setup, Mahjong-Joseph junction, Mahjong mode gamma 1 and gamma 2 at the end of a topological superconductor. The exchange can take place when we increase the magnifiers through the ring, and an audible interface of half side of wire vary from 0 to 2 pi. Let me talk about our ongoing work. In full Kent heterostructure of topological insulator and superconductor proximity, we consider vortex lattice create Mahjong lattice. The dominant force of Mahjong lattice will be Mahjong hopping. However, this hopping can be suppressed by tuning chemical potential right at the center of the gapless surface cone coming from the strong topological insulator. The interaction of four Mahjong fermions dominates. Therefore, we study such a system. Now we have some exact software model in 1D, and we are solving two-dimensional Mahjong interaction lattice. Given symmetries and spatial dimensions, we have studied the minimal model of a bulk and surface Dirac Hamiltonians by Cliff algebra. And topology of the gap system can be obtained by those Dirac Hamiltonian properties. My technique of the Dirac Hamiltonian method is important not only for original tempo classification, but also for classification of the crystallized topological phase. So I use Dirac Hamiltonian method and topological invariant method to do further classification. I classify refractional topological insulator and superconductors, and I also classify the refractional symmetric topological semi-metals and non superconductors. This shows that I am able to study any topological phase with any symmetries in any non-interacting system. One of my important works is classification of refractional symmetric topological insulators and superconductors. I was inspired by the prediction and observation of the crystallized topological insulator that is three-dimensional refractional topological insulator is characterized by Miro's chain number. It turns out this is a starting point of a refractional symmetry topological phases. There are much more refractional symmetry topological phases. Our classification shows all possible topological phases with refractional symmetry, which include insulators and superconductors. The recent discovery of a three-dimensional topological Dirac semi-metal, which is sodium bismuth, inspires to classify refractional symmetric topological semi-metals and nodal superconductors. Our paper shows that the classification of a refractional gapless system depends on the locations of Fermi surfaces. This is similar with the temporal classification of the gapless systems, which is also discussed in our paper. This table shows the classification of Fermi surfaces outside the Miro planes. In the table, this CZ2 invariant, which is defined by the combination symmetry of the refractional symmetry and the time inversal or particle symmetry, is quite interesting. We also can consider Fermi surfaces located at a high symmetry point within the Miro planes. It turns out the classification is just a dimensional shifting of the classification of refraction symmetric gap systems. Also for the Fermi surface of the high symmetry points in the Miro plane, the classification is also dimensional shifting but in the opposite direction. Let me briefly talk about my current projects. First, in the literature, it is hard to find an article talk about the classification of topological quantum matter with symmetry in well-organized matter. Therefore, ChingKai, Andreas, Jeffrey, and I have decided to write an article about classification of non-interacting topological phases in Review of Modern Physics. Our proposal was accepted by APS in April 2014. Now I am writing two parts of this paper. Because I have some background from Mahjong systems, so I'm writing one-dimensional Mahjong chain in class D. And of course, I am writing the crystallized topological insulator and superconductors. Andrea and I have studied refraction topological insulator in anti-perovskite materials. We will also cooperate with experimentalists in Max Planck. So far, according to our tie binding study and the DFT, we see a gapless surface mode in 110 Miro plane. We suspect this gapless surface mode might be protected by non-zero Miro chain number. However, we did not see any gapless surface mode in 100 Miro plane, which does not agree with the Liang Fu recent paper. We are looking for a better way to understand those results. Because my background from Mahjong fermions and topological insulator and superconductors, I would like to extend my research further. I am interested in interacting Mahjong fermion in lattice systems. I am looking in two directions. Is it possible to find a topological order in Mahjong interacting system? Is it possible to realize these systems in the experimental setup? I am also interested in universal quantum computing. It is well known that universal quantum computing is impossible in Mahjong fermion systems without breaking topological protection. Somehow, if topological protection is broken, what is a promising protocol to achieve a universal quantum computing in Mahjong fermion systems? I have plenty of classification tables of topological phases. Propose possible materials to confirm my classification is my plan. There are too many papers about different types of crystallized topological phases. I would like to figure out a way to unify them and provide a complete classification of crystallized topological phases. Thank you for watching this video till the end. I hope this video helped you know more about my research.